going to cover a few topics which are slightly different in this class. The first is towards the end of the last class we were talking about imperfect transfer of momentum from a solid surface to a gas molecule which is impinging on it. Now, if it is a dense gas, then what we would assume is that the transport of momentum between the solid and the gas molecule would be complete. Similarly, let us say we have a heated wall in contact with a gas. So, at the interface between the solid and the gas, we would assume that the complete thermodynamic equilibrium has achieved, and as a result of which the temperature on the solid side of the interface would be equal to the temperature on the gas side of the interface, or in other words there would not be any temperature jump across the interface. So, any molecule which comes from the bulk and strikes the solid will reach thermal equilibrium, thereby attaining the temperature of the solid before it bounces back to the bulk of the gas. But this concept would not be valid when the pressure of the gas is reduced and when we reach the condition such that the continuum limit may not be adhered to. So, whenever we reach the situation of a dilute gas, or in the case where the Knudsen number is rather large, in that case imperfect attainment of equilibrium can give rise to a temperature jump at the interface. So, the concept of accommodation coefficient, which was introduced in the last class, but I could not cover it completely. So, I am going to talk first about the accommodation coefficient and the equation that can be used for the temperature profile of a fluid when it flows through a duct in microsystems. And we are also going to talk about an interesting application of flow at the microscale in the form of creating or fabricating a sensor for fluid velocity. So, how can we design a sensor to measure the flow velocity for fluid velocity, and what are the two different there are two different approaches. One is to measure the temperature of the sensor itself, and the second is to measure the temperature of the surrounding fluid, and from that how one can calibrate the velocity of the fluid flowing past the sensor. So, we will discuss about that. But the main emphasis of today's lecture would be microfluidic networks. That means, if you would like to irrigate, let us say, an area with a number of microchannels. So, obviously, there would be some microchannels which would be the principal source of fluid, of liquid, let us say liquid towards that region, and then you have to have number of branches from the main artery, so to say, from main channel to a number of branches and so on. Now, how do we make these branches? Okay, should we divide them equally, first from 1 to 2 and then from 2 to 4 and so on? And if we do that, what is there a specific ratio, is there a specific geometric ratio that we have to maintain in order to achieve the best possible irrigation at the smallest pressure drop in the system? Because remember, like the moment we have two channels being created from one single channel, there would be some pressure drop, there would be some entry pressure drop at the point where the two channels, where the channel is bifurcated. So, how do we reduce, how do we keep this pressure drop at a minimum, and that would be that we are going to talk about in microfluidic networks. But first, let us talk about accommodation coefficient, which we define as beta, and we are going to talk about two accommodation coefficients, one for the momentum and the other for energy. So, if we think about the thermal accommodation coefficient, the definition is it is the ratio of the average energy which gets actually transferred between a surface and the impinging gas molecules scattered by the surface to the average energy which would theoretically be transferred if the impinging molecules reached thermal equilibrium with the surface. So, obviously, the value of beta will be in many cases will be less than 1, and the impinging molecules will reach thermal equilibrium with the surface if the time of collision is more. Okay. So, in rarefied systems or in systems at low pressure, in systems where the Knudsen number is large, there is a possibility that such equilibrium will not be reached, and therefore the fraction of that fraction is called the accommodation coefficient. So, it is the actual amount of energy transferred in the collision divided by the amount of energy which would have been transferred had there been complete thermal equilibrium at the solid gas interface. When we talk about similar to thermal accommodation coefficient, there is something called transverse momentum accommodation coefficient. So, it is a fraction of momentum normal to the wall which is transferred to the wall in terms of stress. The stress is known more commonly as pressure. So, by creating a pressure on the wall, some of the momentum is lost. So, this TMAC, the transverse momentum accommodation coefficient, takes into account this loss of momentum of a molecule when it strikes another wall. So, for rarefied gases, the velocity at the interface is not equal to 0, rather it is expressed, it is modeled as a function of a slip length and a gradient of velocity at the wall. So, this is used as the boundary condition for rarefied gases, and by rarefied gas we mean when the Knudsen number is greater than 0.01 but less than 0.1. For such cases, the value of velocity at the wall is not 0, it is rather expressed in terms of a property which is called the slip length and the gradient of the velocity at that point. Now, this slip length data are large quantities of data for slip length are available for different fluids under different conditions. So, this slip length obviously can be correlated with the accommodation coefficient beta and the mean free path of the molecule. So, as you can see that when beta is equal to 2, from kinetic theory for continuum regime, we know that in continuum regime there is no the concept of slip does not arise. So, from the definition of the slip length, so from the as is shown as 2 minus beta by beta, the value of beta can be shown from kinetic theory that for continuum, when the continuum approximation is valid, the value of beta is equal to 2 and the value of slip length would be 0, and the condition at the solid gas interface would be the no slip condition. But the value of beta will not be equal to 2 for most of the other cases, and obviously as the mean free path increases, the value of the slip length will also increase, and the mean free path will increase for a system which is rarefied. So, for a rarefied system will have finite slip, and the slip coefficient, the slip length will increase with increase in mean free path. So, experimental data for beta can be found in the literature, and if we know what's the pressure of the system, then we should be able to find out what's the mean free path. So, combining these two, the slip length for velocity at the interface at the solid fluid interface can be evaluated, which will serve as the new boundary condition for solution of equation of motion and many such cases. So, similar to the concept of slip length in fluid flow, there would be some sort of a temperature jump at the wall wall at the wall, and that is the wall temperature jump coefficient, that is denoted by G and is called the wall temperature jump coefficient. So, the temperature at x equal to 0, that means temperature at the interface, if we call that as Tr, which is not going to be equal to Tw, but another quantity is going to be added to it with G as the parameter and the temperature gradient as at the wall being the other factor, and the product of the two will have to be added to T wall, the temperature of the wall, in order to obtain what would be the temperature on the gas side of the interface. So, conceptually the accommodation coefficient gives us the slip length, and if it does so, if accommodation coefficient gives us the slip length, then we should be able to correlate in a similar fashion the temperature jump at the wall defined as Tr minus Tw with a parameter which is called the temperature jump coefficient G, and the gradient of temperature at x equal to 0 for situations, for rarefied situations where the collision between the gas molecule and the solid molecule would not take place for a sufficient length of time for equilibrium, thermal equilibrium, to reach thermal equilibrium at the interface. Now, this temperature jump coefficient G via the kinetic theory can also be obtained via kinetic theory from the concept of thermal accommodation coefficient, a material parameter which is denoted by F, and the mean free path. Okay. So, G is 2 minus gamma, where that is the accommodation coefficient, the F whose formula is given, and the mean free path. So, once we have the value of G, then the temperature jump at the interface can be evaluated. Now, this temperature jump coefficient G, as we have mentioned, can be regarded as an additional distance of the gap. So, if we write the equation for the temperature at the wall, which is T at x equal to 0 is equal to T of the wall plus G times del T by del x at x equal to 0. So, of course, this temperature jump is T at x equals 0 minus Tw, and which would be equal to this term where G is the coefficient. So, what I have drawn here is a situation in which this is a dense gas, and we have the temperature gradient. So, this is the temperature gradient, temperature profile, temperature gradient. This is the wall temperature, which is the same for the solid as well as for the liquid side as well as the gas side interface, and there is a definite drop, and over at the interface also the two temperatures at both sides of the interface are same, and then we have the case. So, this is a case for Knudsen number less than 0.01, such that we have this dense gas situation and there is no temperature jump across the interface. On the other hand, if it is a rarefied gas, then what we find is that this is the temperature on the solid side of the interface, and then we have a temperature, this is on the liquid side of the interface, this is the liquid side interface at the other end, and here we have Tw2. Okay. So, this situation is for a rarefied gas where the Knudsen number is greater than 0.01. Okay. So, this temperature jump at the interface can be thought as if we have an additional distance of the gap. So, what we can think of this to be equivalent to, I have the solid, then as if the solid has been we have another gap. So, this is the solid temperature, this is this imaginary gap, and then I have this temperature. So, it's conceptually easier to understand, to visualize the situation as if the presence of a specific gap, additional gap in this is providing the extra resistance to heat transfer for rarefied gases. So, the other factors which we need to know is that the Nusselt number for constant wall heat temperature is going to be different from that of the constant wall heat flux, and a numerical study indicates that the slip flow model correctly represents convective heat transfer between the continuum and the molecular flow. So, whenever continuum model breaks down, the use of slip flow model correctly represents heat transfer between heat transfer for such cases. And in microchannel flows, we also need to consider the effect of axial heat conduction, but generally the viscous heat dissipation and the expansion cooling can be neglected. Now, we come into one of the applications of convective cooling for flow measurement. We all know that as the flow over a hot surface is increased, we are increasing heat loss from the solid. So, is there a way to relate the cooling achieved due to an enhanced flow on a solid substrate, and more importantly, can that be used as a sensor to measure the velocity of the flowing fluid? Okay. So, in order to design such a sensor, certain considerations will have to be kept in mind, and the governing equations for such cases need to be clearly stated. So, what we are going to look at is the construction of a thermal flow sensor, which consists mainly of the heating element and temperature sensors that measures the temperature of the heater and the fluid before and after the heater. So, let us say what we have in this case is I have a heater embedded into a solid. So, this is my heater, this zone is the heater, and it's situated in a channel, okay, and I have a temperature sensor over before the heater and at equal distance after the heater. Okay. So, when we have no flow in the system, then what we have is a temperature profile which so I have some heat which is being added to the system, and I can draw the temperature profiles which are going to be symmetric in shape. But this symmetry is going to be disturbed the moment I am going to have a flow present in the system. So, the moment I have a flow in the system, then the profile will look something like this. So, as if everything will shift towards the right. Now, here also I am going to measure the temperature in using these two sensors. Now, what happens then? We are going to find out the governing equations. We are going to write the governing equations for flow for heat loss from this plate. Now, if you think carefully, the heat loss from this plate would be into the fluid, but some heat will also be conducted into the solid. So, there is going to be, so the total amount of heat which is being supplied to the heater will have a convective contribution, we will have some convective losses, plus there will be some conductive losses from the heater to the solid. Now, this convective heat loss is going to be a function of the fluid velocity. So, we are going to see what are the what is going to be the functional form of Q convection in such a case. Whereas, in the case of Q conductive, it is going to depend on the thermal conductivity, it is going to depend on the temperature difference and so on. So, this is a material property, this is a condition, whereas over here this is going to be a function of the velocity, and that would allow us, if we can calibrate properly, that would allow us to find out what's going to be the velocity of the situation. So, if we look at the complete sensor arrangement, it involves fluid flow, heat transfer and thermoelectric energy, and we will also need to do some sort of signal conversion in order to achieve this. So, the basic sensor setups can be of two types. One is the basic sensor setup is that the heating of the fluid, it's going to impose a temperature profile in the channel or near the wall, which is measured at certain position by thermocouples or some such sensors. The fluid flow cools the heater where temperature and electrical properties are measured. So, let us look at the energy balance for such cases. Now, if you see that the total power lost by the heater is a function of Q convection and a function of Q conduction, which are the first and the second terms of the equation that I have written, where TH and TS and TF are the temperature of the heater, the substrate and the bulk fluid. So, TH minus TS provides the driving force for conductive heat transfer in the solid, whereas TH minus TF provides the gradient necessary for convective flow. Now, GS and GF are two coefficients, one refers to conduction and the other refers to the convective heat transfer coefficient. The flow measurement essentially relies on the variation of GF with the fluid flow and is calibrated. So, we know that from our calibration that for the value of GF to be this, what would be the corresponding velocity of the fluid. So, from that one can find out what is the velocity of the fluid. Now, wall heat transfer from the heater evaluates the energy of heating the fluid and increasing its temperature. Now, if you look at the last equation, the heat dissipation into the substrate, if it is Qs, then the total power provided to the heater is a sum of Qs, which is the heat dissipation of the into the solid substrate, plus rho of the fluid, Cp of the fluid, area of the heater times T of the heater minus Tf multiplied by W, where W is the velocity. So, this gives us the complete picture, complete figure of complete equation for the heat loss from the sensor surface. Now, if you use convective cooling for an electrical heater and you measure the temperature according to the second method that we have just discussed, it involves lesser errors. So, what we do is we do not have to measure in the second method, we do not have to measure the temperature of the fluid at different points, which is difficult. Rather, we measure what is the temperature of the solid at different points. So, as we understand that with increase in flow, we are going to provide more heat to the sensor, and if we provide more, if we lose more heat through the sensor, then these solid temperatures should also vary, and the variation of the solid temperature will provide us the knowledge about how much of heat is being lost. So, it's a much better method to measure the temperature of the solid compared to the temperature of the fluid over here. So, as a result of which most of the sensors that we see are located on a membrane, and this minimizes the parasitic heat losses and increases the sensor accuracy. So, these are some of the basic equations which are given in any textbook, and here I am referring to the textbook by Kaufman, Transport Phenomena in Microprocess Engineering. So, I have collected the equations from there. So, what you see first is the heat loss to the fluid. So, it is Th minus Tf is the driving force, and when you and alpha is the heat transfer coefficient. So, if you think of the flow to be laminar over the heater, which in most cases of microchannels it is going to be laminar flow. So, the Nusselt number, point value of the Nusselt number is simply equal to 0.332 Prandtl to the power 1/3 Reynolds to the power half, and if we integrate this Nusselt expression for Nusselt number over the entire length of the heater, what we get is Nusselt number based on the entire length to be equal to 0.664 Prandtl to the power 1/3 and Reynolds to the power half. So, in this case the Reynolds number refers to Reynolds number is based on the entire length of the heater. So, putting the value of heat transfer coefficient in the first equation, one can obtain the heat lost over the heater area to be expressed in terms of lambda, the property, Prandtl number, the similarity parameter, and all the other things. So, the total power which is dissipated by the heater is given by the last equation in terms of quantities, in terms of all the quantities which can be measured. So, the temperatures to be measured are temperature of the heater, temperature of the solid, and then the rest are dependent on the velocity and the thermophysical property of the fluid. So, this way once this is calibrated this way, a detailed analysis of such a correlation requires many parameters. So, if you look at the previous expression, then you would see that a large number of measurements are to be carried out. The physical properties at different values of temperatures are to be known, and then only one can use this expression to find out what is the total power loss from such an heater. So, in order to extend the use of this, in order to ease the use of such a relation, a correlation of the following form is proposed and is used in most of the calculations, which simply tells us that the correlations are, that is, two coefficients C1 plus C2 into W, which is the velocity, to the power half T of the heater minus T of the fluid. So, both these coefficients are calculated, are evaluated from calibration measurements, and therefore, you should be able to obtain from the known value of P and from the measured value of the temperatures the unknown value of W, which is the flow velocity, and that is the purpose of the flow sensor. So, C1 and C2 are already known to us. So, measuring the two temperatures and the power input to the heater, we would be able to obtain what is the unknown value of the fluid flow velocity. Now, we come to an interesting part of it, which is what I wanted to discuss in this class, is the microfluidic networks for heat exchange. Now, conductive and convective transfer of a species or energy is the focus of creating microfluidic networks. So, it can be used for heat exchange, it can very well be used for mass transfer as well. So, when we talk about fluid flow in microchannels, it is a conductive transport which dominates over the which is dominating. Now, you can have secondary transversal flow, especially when you have an obstruction in the path of the flow, or obstruction which is perpendicular to the direction of flow, or you have a bend in the path of the fluid, thereby causing secondary flows. For example, Deign flow which one can encounter whenever there is a 90-degree or some such bend, and which depends on the Reynolds number, and which also depends on the dimension of the channel and the radius of curvature of the bend. So that's how Deign number is defined. It's Reynolds number times d by the radius of curvature to the power half. So these kind of secondary flows increase the value of heat or mass transfer. Now the counterflow rate, since the requirement here is small diameter channels with a short diffusion length and creation of secondary flow structures. So if we can achieve that, if we can have a small diameter channel whose diffusion length is obviously small, and if we can create a number of secondary flow structures, then we are going to get both conductive and convective flow, and we have we can enhance the transport process. Now the major drawback of some of these processes is the flow rates are going to be extremely small. So if you think of a single element of a microchannel, the amount of liquid it can handle is going to be very small. So even though the diffusion length is small, and therefore you can have very high transport rates in between two species or very high heat transfer rate, but the small size of the device means that you can handle very small quantities of fluid at a time. So you can increase that by having a large number of such channels connected parallelly. Okay. But you can do internal and external numbering up or equal up of the desired effects to enhance the rates which are possible in such cases. But this internal or external numbering up or the equal up process needs space, and uniform distribution of fluid into all these parallel channels is a major challenge. So the space and the distribution, these two limit the use of numbering up or equal up strategies to counter the small quantities of fluids which can be handled at a time. So we are going to look at what's the status of microfluidic networks for device cooling. Now obviously what we would like to do is to provide high thermal performance with low pressure loss. So one such requirement is the cooling of electronic components, and mostly long straight channels are used. Now the long straight channels are relatively easy to fabricate, so there is no question of no problem of distribution of liquid, but the problem is this has relatively low heat transfer coefficients. To give you an example, the maximum heat dissipation rate is of the order of 10 megawatt per meter square for single phase liquid flow. Okay. But so in order to reach to all the places, one needs to have a number of branches from the main channel, from the principal channel, so as to spread fluid over an area. And you not only have to spread the fluid over an area, you have to collect it again. And how do you make these branches? It depends. It is governed by the constructal theory of Deign. So the constructal theory of Deign is extremely interesting. So the constructal design approach, it begins with the smallest element on zero level and connects these with those on the next higher level, and this is very common in biological systems. Think about all the arterial network that we have in our system. Okay. So the arterial network, the smallest of these arteries, the capillaries, reach each and every cell of our body. So from a tiny capillary, then it's going to join with another one, so that becomes the building block of the entire blood circulation system in our body. So from the tiniest capillary, they combine and form the next level of blood vessels, and those very small blood vessels keep on combining till we have the major arteries that supply blood from our heart to the remotest place of our body. So, the constructal theory of Deign mimics the natural process, mimics what is already available or already known, already established in biological system, and tries to apply it for uniform distribution of fluid over a hot surface such that it can be cooled convectively and collects the hot liquid once again at the end of the process and brings it back to the point from where it starts its movement towards the hot surface once again. So, in nature the systems have a finite smallest size, and therefore they follow the constructal approach. The question is, how do we find out the optimum size of channel elements and the corresponding area covered? So, here we come across a very interesting law which is known as the Murray's law. It simply tells us that the optimum flow distribution and the cross sections of the channels on different branching levels are influenced by a biological principle which is known as the Murray's law. It is applicable for in the branching of blood vessels or plant capillaries. Now, when you see our body as a system, many of the finally what the size of the arteries and size of the vessels, they are in the microscale. So, what our heart does, it pumps blood from the heart to every section of our body. Now, when it does that, the blood which flows from the heart encounters a number of branching out at different places. So, from the main aorta, it divides into two, and the two divides into another two, and so on. At each of these branching, there would be some pressure loss, but in order for a healthy heart, in order for the heart to do minimum amount of work, this branching should be such that the pressure drop due to this branching is the smallest. And when researchers compared the sizes of the branches with that of the mother artery, what they have found out is that if D1 and D2 are the diameters of the two branches and D3 is that of the mother artery, then D1 cube plus D2 cube is equal to D3 cube. And it has been mathematically shown that when the branching out follows this rule, that D cube is equal to D1 cube plus D2 cube, the pressure drop in such systems would be the least. And that is what this was observed by Murray, and he proposed it as a law which is known as the Murray's law. And what it simply tells us is that it is the sum of the inner radii to the power of 3 on each branching level is constant, then the channel network will need minimal power consumption or exhibit minimal pressure loss for a given flow rate. And it's amazing to think that all branches in our body follow Murray's law. So, what has been proposed is that the same law now can be used for branching out of microfluidic channels as well. Now, so symmetrical bifurcation, the Murray's law gives the correlation for the diameters on various branching levels. So, if we have D3, so the first equation, if we see that D3n, that is dn cube is equal to 2 to the power z when there are z number of bifurcations, and dz cube. Okay, so this, whenever there is any branching that is done on a system, it must follow Murray's law. and some of the examples of Murray's law are amazing, and I will try to draw this two level heat exchanger network from branch channels. Is that one, you start with one channel, you create two channels, then these two channels will create another two, and this is going to create one more channel. Okay. So, this is going to be an unit. So, this is the setup of a two level heat exchanger network from branched channels, and the way it is done is, let us say this is the main channel through which the liquid is being pumped, and then we are going to have a branching at this level, a branching at this level, and so on, and there will be this unit will be repeated over here, and over here. So, if you take the complete diagram, you would see that these will later on be combined. So, this is the region which you would like to cool, and they are going to be combined into one. These are going, at the end they are going to be combined into one, then these two are also will be combined into one. But at every stage, at every point of branching out and the point where they are going to be combined, so that I can have flow again from here, at every point Murray's law will have to be maintained in order to obtain the minimum pressure drop. So, this relation serves for an equal wall shear stress in the channels on each branching level. So, this is branching level 1 and this is branching level 2. So, we have a two level branching and then two level combination in order to irrigate a space on a solid to lower its temperature. So, what are the single channel element calculations? We are already familiar with some of them. So, we need to look at the design rules and correlations for high performance heat exchangers and microchannel networks. So, if it is laminar, fully developed and constant heat flux case, then the Nusselt number is a constant equal to 4.3. But if we have the entrance or if we have a bend, then the straight laminar flow is disturbed. What we then have just after a bend or near the entrance, developing flow taking place, and this developing flow with the appearance of additional pressure loss is going to enhance the transport process in the channel, and this enhancement is given as the equation suggests. A Nusselt number m e is equal to Nusselt number m, where the Nusselt number m, the right hand side, denotes where the flow is fully developed, and the left hand side suggests it is the Nusselt number for the developing flow, and these two are connected in terms of Prandtl number, which is a thermophysical property of the liquid, and x star, which is a dimensionless entry length. So, with the dimensionless entry length x star given as L, which is the length of the channel, dH, which is the hydraulic diameter, and Peclet number, which is the product of Reynolds into Prandtl number when we are talking about heat transfer, and for mass transfer Peclet number, it would be the product of Reynolds and Schmidt number, and one can obtain from this what would be the optimum channel length for such cases. So, just to give you an example, in order to obtain a heat transfer enhancement of 30% such that Nusselt number m e, the Nusselt number for the developing flow, or the Nusselt number when there are number of bends present in the flow path, divided by Nusselt number m, which is the fully developed condition, to be equal to 1.3, the entire length divided by the hydraulic diameter if you look at the left hand side of it, the entire length divided by the hydraulic diameter should be less than 0.005 Reynolds number. So, this gives a very good handle on the design, on the efficient design of a microchannel, which would provide certain quantity, certain amount of heat transfer or mass transfer enhancement. So, this tells us precisely what in order to obtain X percentage of heat transfer enhancement, the entire length divided by the hydraulic diameter X by dH should be less than 0.005 Reynolds number. So, you know, if you know your Reynolds number, if you know the value of dH, then you know what would be the entrance length to obtain a certain percentage of heat transfer enhancement. But there is obviously a limit to this. If you use a longer channel, then the pressure loss increases without any additional benefit to heat transfer. So, simulation of heat transfer in a microchannel with constant heat flux and with curved flow at bends, they demonstrate certain interesting trends which we have already discussed, but I am summarizing it over here. So, if you have flow in a microchannel under constant heat flux condition, and the curved there are bends present in the path, and there is a curved flow. What you see first is the existence of vortices which are all at the bends, which is called Deign flow. So, the existence of Deign flow can be seen from the numerical simulations. The heat transfer enhancement, there would be heat transfer enhancement just after the bend, and once you have such enhancement and such existence of vortices, the phenomena will be dampened by the viscous forces present in the path. So, viscous forces present in the fluid. So, any vortices which is the primary cause of heat transfer enhancement will be dampened, and there will be reintroduction of laminar flow in the straight portion of the pipe after the bend. Now, whenever you have straight portion of the pipe, the viscous forces will force all these vortices to bring back laminarity in the system once again. So, any enhancement of heat transfer, any enhancement of transport process that you may get will be nullified, will be dampened once you move away from the bend. And finally, the Nusselt number will asymptotically approach the value of the laminar flow in straight channels once you flow past the such bends. So, if you have combined channel elements, then what you would want is low pressure loss and low mean driving temperature difference, so that you can enhance the performance of a heat exchanger. Now, both these effects lead to geometrical optimization of dendritic channel networks, which follows Murray's law, and which is under the broad concept of Bejon's constructal theory, and this ensures minimum entropy generation. And once you have minimum entropy generation, then that is the optimum channel network that you can think of. So, you work with single channel to get the maximum amount of heat transfer enhancement, and then combine the channels as per Bejon's theory, as per Murray's law, to create more and more to create a network of channels which will have the advantage of high transfer rate and at the same time the least possible pressure drop. So, these are the points which need to be kept into mind while designing a microfluidic network. And when we think about heat exchanger channel networks, so from branched channels, we need to combine the branched elements from 0 level to the desired covered area. Whatever area that we would like to cover, we are going to combine the branched elements. The channel dimensions and the covered area are determined by the actual situation. The channel cross sections are going to follow Murray's law. Now, when we would like to optimize a channel network, we are going to follow whatever is present in biological systems, such as in you and me, and thereby obtain the channel dimensions. When we design a micro heat exchanger device, we have already covered what are the balance equations for cooling, for heating, the transfer correlations, mostly assuming laminar flow, and we know that these expressions are valid independent of the length scale. So, these expressions can be used for microchannels as well. Now, there are obviously two different approaches, the LMTD method and the epsilon NTU method while designing a heat exchanger, and any of these methods can be followed depending on the situation at hand. So, just to give you an idea that what are the typical overall heat transfer coefficients of microstructured heat exchangers, they range from 2.6 kilowatt per meter square for gas liquid to 26 kilowatt per meter square for liquid flow. Now, if you compare that with the best conventional heat exchangers that we plate heat exchangers that we can have, they also exhibit very good heat transfer, but they range from 0.2 to 2.5 kilowatt per meter square per Kelvin under optimum conditions, and maybe up to 5 kilowatt per meter square per Kelvin for liquid flow. So, if you see the advantage of a micro heat exchanger, you would get about it's 5 times more efficient. It can extract 5 times more heat from a region compared to a plate type heat exchanger. So, that is the unique feature, unique advantage of a micro heat exchanger in or any microscale device which has initiated such intense research in recent years in the field of microscale transport processes. Not only newer and newer devices are being fabricated, being invented, or there would be tremendous there is a tremendous development in the design of microstructured devices, but to understand the basic physics of the process, it's an area of intense research activity, and which will continue for quite some time, because we still haven't reached the point where we cannot go any smaller. So, from micro device we are probably going towards a nano device. The problem that we have is how to fabricate it, how to make the system leak proof, how to reduce the pressure drop, that is one of the major problems, and how do we distribute the liquid, how do we distribute the fluid evenly in all the channels. So, these are some of the major drawbacks. So, and the design issues, if we think about the design issues for exchange equipment, when we consider heat transfer, it is the axial heat conduction in the relatively thick walls which reduces the delta T available, and if it reduces the delta T, then our process efficiency gets hampered. How do we distribute it equally in all channels? Okay, and another important thing that I haven't spoken before is fouling or blocking of single passage or complete parts. It is not possible in most of the cases to clean a microchannel once it gets fouled or it is blocked by the presence of suspended particles. So, these are some of the issues that one has to keep in mind during design and operation. So, as a summary, what I am going to talk, what I can say is that the microstructured equipment, they are promising, and there are many successful applications where microstructured micro devices have been effectively utilized. The major reason why such devices are so successful is the high gradients, high surface area to volume ratio, and there are various construction materials depending on the application. So, if you have so many construction materials for each specific use, and such high gradients allows the use of such devices in a variety of situations. So, it is very flexible, its range of applicability is quite large, and the characteristic dimensions of such devices are comparable to the thickness of the boundary layers. Now, that is one of the reasons why these devices offer such high transport rates. So, there is no region which is unutilized, where the concentration is the same, where the concentration is uniform or the temperature is uniform. Throughout, everywhere in the device is performing its transferring heat or transferring mass. So, thereby the entire volume, entire cross section of the device is being utilized, and integration of various elements, they enhance and they guide the entire process. So, there are definitely huge opportunity in the area of process intensification, in the area of new technologies. So far we have discussed so many positive as well as some of the limitations of micro scale processes, micro scale devices, and we may think that we have invented so many things. We know so much about micro scale processes. Our fabrication techniques are so wonderful that we would be able to make almost anything that we want with the property that we desire, and we can have fantastic applications out of them. But just to bring you back to reality, I would like to show one picture, and that would tell us how far behind to nature we are in terms of the design and fabrication of microfluidic devices. So, the next figure, if you see, I mean all of you can identify this. This is the picture of a dried leaf, and if you look at some of the major channels, some of the major paths for the leaf to receive nutrients from the main tree, you would be amazed. We can never think of making a leaf with such intricate microfluidic channels carrying different fluids at all parts of the leaf with the best technology that we have today. So, sometimes it's good to know where we stand in terms of nature. Thank you.